Hello, this is Chetan Sherpa, and this is my presentation on the data structure Cartesian tree. In the introduction, I have noted that the creators of the Cartesian tree are Seidel and Aragon, who created it in 1989. The Cartesian tree is a data structure that can answer range queries by finding least common ancestors in the particular tree. What makes this tree interesting and different from other trees is that it has both the properties of a binary tree and a binary heap. We'll talk more about that in the following points. So, using the tree property, the Cartesian tree is formed from a sequence having a node for each number in that sequence. So Cartesian tree helps to the tree property helps to input the values into the tree. And the heap property helps to sort the inputted data. And to use a heap property, the tree must either be in a maximum heap or a minimum heap. In the case that it's in a minimum heap, each node must have a value greater than its parent. And in the case that it's a maximum heap, each node must have a value smaller than its parent. In the final note, I have noted that an in-order traversal of the tree would give the original sequence used to form the tree, meaning that once the user inputs data in the tree, at the end of the code, at the end, you will be given the sequence in the exact same sequence of the original sequence. We'll talk more about that once I illustrate it on the diagram. Now, talking about the properties of a Cartesian tree. The Cartesian tree is not height balanced, meaning that this tree subtrees differs with height more than 1. Next, this data structure consists of nodes which maintain two important values, the data field and the priority field. Now, the data field helps to store data in the tree, while the priority field helps to sort the data in such a way that the tree is proportional. To be ordered, the data field uses binary search tree properties and the priority field uses heap order properties. Being more specific, the tree data structure stores values in terms of x and y. This makes it a binary search tree with the value x and the binary heap with value y. Finally, this data structure allows users to uniquely specify the tree being constructed, and the priority field takes a big role in this. Now, in the case that the tree is in a maximum heap, in order to maintain that heap, the first node in the left subtree must have data fields that are less than the data field of the root. Secondly, the nodes in the right subtree of the root must have data fields that are greater than the data field of the root. In the minimum heap case, the priority value of the root is greater than the priority value of its children. This way, it is properly sorted in the way n of maximum heap representation. So in the case that it is a minimum heap, as same as the maximum heap, the first two steps are the same. The nodes in the left subtree of the root must have data fields that are less than the data field of the root, and the nodes in the right subtree of the root must have data fields that are greater than the data field of the root. What's different is the priority value of the root is smaller than the priority value of its children. This way, a minimum heap can be represented. Now, this is the representation of both the maximum and minimum heap. Looking at the diagram for the maximum heap, we can see that 40 is the root node, 5 and 10 is on the left subtree, and 30 and 28 is on the right subtree. Looking at the diagram, we can conclude that the in-order traversal of the input values will be 5, 10, 40, 30, and 28, which is the same as the initial input sequence. This clarifies what I was pointing out in the introduction of this video. And we can also see that each node in the maximum heap has a value smaller than its parent. In the case of the minimum heap, we can see that each node has a value greater than its parent. But also in the minimum heap, we can observe that the inner order traversal of the values is the same. It's 5, 10, 40, 30, 28, which is the same as the initial input sequence. Now, we've talked about the introduction and properties of Cartesian tree, but let's talk more about the uses of Cartesian tree, because that's more important. So, at first it is used as a binary search tree for a regular order sequence. But it's mainly used in range search problems, which typically involves queries asking least common ancestors in the tree. And it is also used to construct a suffix tree. Now, if you don't know what a suffix tree does, it is used to analyze text strings, which is extremely important. Now, furthermore, we are talking about the time and space complexity. So, the space complexity for all the Cartesian tree is O(n), and the average and worst case time complexity are as given below. The axis function has no time and space no time complexity, but the search has the average time complexity of log n and the worst case of O(n). The insertion function has the same, with the average case being log n and the worst case being O(n). Likewise, the deletion is the same, with the average being log n and the worst being O(n). That's the end of this video. I hope you understood what a Cartesian tree does and hope it helps you in the future. Thank you.